Welcome to today's journey into the most mysterious objects in our universe, black holes. These cosmic giants are unlike anything else we know. They bend space, twist time, and defy our common sense asterisk. Imagine a star many times more massive than our Sun. For millions of years, it burns brightly, fusing hydrogen into helium, producing enormous amounts of energy. But eventually, the star runs out of fuel. When this happens, the delicate balance between the outward push of fusion and the inward pull of gravity collapses. The star implodes under its own weight, crushing all its matter into an unimaginably tiny point called a singularity. Around it forms an invisible boundary known as the event horizon. This is the point of no return. Once something crosses it, whether it's a star, a spaceship, or even light itself, it can never come back. To picture this, think of space-time as a giant fabric. Most objects like planets or stars make small dents in this fabric, but a black hole is so heavy that it punches an endless hole straight through. Scientists classify black holes into several categories. Stellar black holes, a few times the mass of our Sun. Intermediate black holes, hundreds or thousands of solar masses. Supermassive black holes, millions or billions of times the Sun's mass, sitting at the center of galaxies. Our own Milky Way hides one called Sagittarius A, and possibly primordial black holes, tiny black holes formed just after the Big Bang. What makes black holes fascinating is not just their existence, but how they stretch the very laws of physics. Now, let's imagine a brave astronaut deciding to approach a black hole from far away. The black hole looks harmless, just a dark sphere, surrounded by glowing gas and dust spiraling around it. But as the astronaut gets closer, things get strange. If we as outside observers watch them fall, something eerie happens. We never actually see them cross the event horizon. Instead, they appear to freeze at the edge, their image fading, stretched and reddened by the extreme pull of gravity. To us, time for them slows down more and more until they seem frozen forever. But for the astronaut themselves, time feels normal. They pass through the event horizon without noticing any sudden change. No wall, no barrier, just darkness all around. Inside, however, the laws of physics twist space and time swap roles. Going deeper is no longer a choice. It becomes as inevitable as moving forward in time. Here comes the terrifying part: what actually happens to the astronaut's body. Close to a black hole, gravity isn't the same everywhere. The astronaut's feet, being closer, feel a stronger pull than their head. This difference stretches their body like a piece of spaghetti. Scientists literally call this process spaghettification. For a small black hole, this stretching would be fatal. Long before crossing the event horizon, the astronaut would be torn apart molecule by molecule. But if it's a supermassive black hole, like the one in our galaxy's center, the situation changes. The tidal forces at the horizon are weaker, so the astronaut might cross the event horizon intact. They wouldn't even notice the exact moment they pass the point of no return. But as they fall deeper, spaghettification would eventually take hold, pulling them apart atom by atom. Now comes the big question: could they escape? According to Einstein's theory of general relativity, the answer is no. Once you're past the event horizon, every possible path forward leads deeper inside. No rocket engine, no technology, not even light can climb out. However, physicists are still debating what truly happens at the core of a black hole. Some theories suggest that the singularity may not be the ultimate end. Instead, it could connect to another place or another universe, a so-called wormhole. If that's true, perhaps falling into a black hole doesn't mean destruction, but passage to somewhere else. Still, this is speculation. Our best evidence says survival and escape are impossible